10.4 ideal gas equation. So far we've seen that volume is proportional to 1 over the pressure, or we could reword that and say that volume and pressure are inversely related. This was Boyle's law. We know that volume is proportional to temperature. Charles' law says that when the volume goes up, the temperature goes up, or if you heat something, it expands. If you cool something, it contracts. And we also know that volume is proportional to the moles of a gas, which is Avogadro's law. So if we combine these theories, then we get this representation, that volume is proportional to the number of moles of gas times the temperature divided by the pressure. The constant of proportionality is known as R, or the gas law constant, and it can be expressed in many different units. Most commonly, you'll see it in the first unit listed here, and that's liter atmospheres per mole Kelvin, and the numeric value is 0.08206. So if you're doing a calculation involving the ideal gas law, and you want to use this constant for your R value, then your volume must be in liters, your pressure must be in atmospheres, and then your temperature must be in Kelvin for all gas law calculations. So if we adjust the relationship, we can move the equation around and adjust some variable positions and come up with the ideal gas equation, which is PV equals nRT. And we're going to practice using that equation in sample exercise 10.4. Sodium carbonate decomposes upon heating to give calcium oxide and carbon dioxide. A sample of calcium carbonate is decomposed and the carbon dioxide is collected in a 250 milliliter flask. After the decomposition is complete, the gas has a pressure of 1.3 atmospheres at a temperature of 31 degrees Celsius. How many moles of carbon dioxide gas were generated? So we're given the volume, the pressure, and the temperature of a sample of carbon dioxide gas and asked to calculate the number of moles of carbon dioxide in the sample. So we are given V, P, and T, and we can solve for N, again making sure that the temperature has been converted to Kelvin, as you see here. 31 plus 273 equals 304 Kelvin. You do not have to rearrange the equation into this form of it, but you can. You can simply use PV equals nRT, plug the values in, and solve it algebraically. You do not have to rearrange the equation. So our final answer is using our ideal gas law constant, and again, the right units are very important here. So our R value, 0.0821 liter atmosphere per mole Kelvin. Notice that the volume is in liters, the pressure is in atmospheres, and the temperature is in Kelvin. Everything cancels except for moles. So units are extremely important. And we get an answer here of 0.013 moles of carbon dioxide. Please do the practice exercise. Tennis balls are usually filled with air or nitrogen gas to a pressure above atmospheric pressure to increase their bounce. If a particular tennis ball has a volume of 144 cubic centimeters and contains 0.33 grams of nitrogen gas, what's the pressure inside of the ball at room temperature or 24 degrees Celsius? Sample exercise 10.5, calculating the effective temperature changes on pressure. The gas pressure in an aerosol can is 1.5 atmospheres at room temperature or 25 degrees Celsius. Assuming that the gas inside obeys the ideal gas equation, what would the pressure be if the can were heated to 450 degrees Celsius? So we have our values tabulated here. We have the initial pressure given and the initial temperature given, and we're given the final temperature and we're asked to calculate the final pressure. So we can use P1 over T1 equals P2 over T2 to solve this problem. Or we could use the ideal gas law and plug in constant variables, constant values for the volume. That would just cancel out. And I think it's better to stick with Charles' law, or I'm sorry, Gay-Lussac's law, P1 over T1 equals P2 over T2. So again, they are rearranging the equation to solve for P2 algebraically, but you don't have to do that. You can plug your values in and cross multiply and get the correct value. Again, make sure that your temperatures are in Kelvin when you do all gas law calculations. So a large natural gas storage tank is arranged so that the pressure is maintained at 2.20 atmospheres. On a cold day in December when the temperature is 15 below, or negative 15 degrees Celsius or 4 degrees Fahrenheit, that's really cold, the volume of gas in the tank is 3.25 times 10 to the third meters cubed. What's the volume of the same quantity of gas on a warm July day when the temperature is 31 degrees Celsius or 88 degrees Fahrenheit? So when you're solving this problem, I want you to think about the kinetic molecular theory, about the molecules and how fast or how slow they're moving depending on temperature, how many collisions there would be inside of the tank, and justify your answer to this problem. 10.6, calculating the effect of changing pressure and temperature on the volume of a gas. So this time we're going to change two variables to see what will happen here. An inflated balloon has a volume of 60 liters at sea level, 1 atmosphere of pressure, and is allowed to ascend in altitude until the pressure is 0.45 atmospheres. During the ascent, the temperature of the gas falls from 22 degrees to negative 21 degrees. Calculate the volume of the balloon at its final altitude. So there's a lot of information, and it really does help to plan or to tabulate your information. So here we can see in this table, our initial conditions are standard atmosphere, 1 atmosphere. And when you release the balloon, it goes up in altitude, and we know that pressure decreases as you go up in altitude. It also tends to get colder when you go up in altitude, so we can see that the temperature is dropping. Now we have two different theories to think about here. The first one is if the pressure decreases, then the volume should increase, and that would be Boyle's law. But if we think about the temperature is decreasing. And when we cool something, they usually contract. So according to the temperature change, the balloon should get smaller. So according to these values, the balloon's going to get bigger. And according to these values, the balloon will get smaller. So we have to figure out which one, the pressure or the temperature, is going to have a greater effect on that change. This looks a little bit confusing, but what they're essentially doing here is using the combined gas law, P1 V1 over T1 equals P2 V2 over T2, and then solving for V2. So this is just the combined gas law being rearranged. And we see that our answer is 11 liters, which means that the balloon expanded. And since the balloon expanded, we can say then that the pressure had a greater effect on the volume of the balloon. Okay, for practice, a 0.5 mole sample of oxygen gas is confined at 0 degrees Celsius in a cylinder with a movable piston, such as that shown in figure 10.12 in your textbook. It's just a piston that is movable. The gas has an initial pressure of 1 atmosphere. The piston then compresses the gas so that its final volume is half of the initial volume. The final pressure of the gas is 2.2 atmospheres. What is the final temperature of the gas in degrees Celsius? Now, in this problem, they don't give you the volume of the gas. It tells you that the final volume is half of the initial. So pick a number, pick a value, and then have that value. So you might say that the initial volume is 10 liters and that the final volume is 5 liters. It doesn't matter which values you use as long as the final volume is half of the initial volume. And again, making sure that you do all calculations in Kelvin. And then if they want the Celsius temperature, you can then convert it back after you're done with the calculation.